Hello again, everyone, and welcome to Lecture 7 of Pre-Calculus Algebra. In this lecture, we're going to be talking about graphing equations in two variables. So let's look at some examples. The equation y squared equals x squared plus 1. The equation y equals x squared minus 3x plus 1. The equation y equals 1 over x minus 1. Are all examples of equations in two variables. Each equation contains exactly two variables. In this case, each equation contains the variables x and y. So these are examples of what equations in two variables look like. Next, we'll talk about the graph of an equation in two variables. The graph of an equation in two variables, in this case x and y, the graph of an equation in two variables is the set of all points xy in the xy plane which make the equation true. Now, I said a graph of an equation in two variables is the set of all points x and y which make the equation true. And when I say all points, each point that I refer to is an ordered pair. So when I say the word point and I'm talking about a function of two variables, every point is an ordered pair. So I could say the graph of an equation in two variables, x and y, is the set of all ordered pairs, xy, which make the equation true. And as an example, I have the equation in two variables, y equals x squared. This is the graph of y equals x squared. This graph is the set of all ordered pairs, xy, in the xy plane which make the equation true. Now, right now, we're probably wondering, well, how do we know this is what the graph looks like? How do we know that this is the set of all ordered pairs in the xy plane that make this equation true? Well, one thing we can do is just take some ordered pairs that are on the graph and confirm that they do make the equation true. That's not going to answer our question completely, but at least it will instill some confidence in us that, yes, this picture, this set of points actually is the solution of the equation y equals x squared. Let's look at this point. X equals 0, y equals 0. Does this ordered pair serve as a solution for that equation? If we take x equals 0 and square it, we get 0. So we have 0 on the right-hand side of the equation. If we take y equals 0 and put it in for y on the left side of the equation, we have 0 equals 0. Okay, the equation is true when x is 0 and y is 0. What about this point or this ordered pair? X is 1 and y is 1. Does this ordered pair also work? Let's try it. If we substitute 1 in for x, we get 1 squared on the right, which is 1. And when we substitute 1 for y on the left, we get 1. You know what? Let me write each of these out. Let me start again with the point 0, 0. we have y equals x squared. And so we're going to take 0 for x, and we're going to take 0 for y. Does this ordered pair make the equation true? 0 equals 0? It sure does. Let's try another example. We have the point x equal 1, y equal 1 on the graph. Let's try that. Does this ordered pair make the equation y equal x squared true? Well, let's see. Let's take 1 and substitute it for x. Let's take 1 and substitute it for y. Is 1 equal to 1 squared? It sure is. Okay. Very good. Now let's take this point, x equal -1, y equal +1. Is this ordered pair a solution of the equation? Let's see. We take -1 and substitute that in for x. So we'll have -1 squared. We take +1 and substitute it in for y, so that will be 1. Now, is it true that 1 equals -1 squared? Yeah, -1 squared is +1, so we have +1 equals +1. That works. Let's take this point, which I say is on the graph, and I say the graph is the solution of the equation y equal x squared. Let's take this point. X equals 2 and y equals 4. Does that make the equation y equal x squared true? Well, let me take x equal 2 and substitute it in for x. So I'll have 2 squared. Let me take 4 and substitute it in for y, so I'll have y equals 4. Is it true that 4 equals 2 squared? It sure is. So the ordered pair 2, 4 is a solution of y equals x squared. And as a last example, let's take this point. X equal -2, y equals +4. Is this ordered pair a solution of the equation y equals x squared? Well, let's see. Let's take x equal -2 and substitute it in for x. So we have -2 substituted for x. And we have 4, y equals 4. We'll substitute that in for y. Is it true that -4 equals, is it true that 4 equals -2 squared? It sure is. So the ordered pair -2, +4 is a solution of the equation y equal x squared. But how do I know that all of these points on the graph in between the point 1, 1 and the point 2, 4 are solutions? Well, let's see. How do we know for sure? That'll take some explaining. How did we come up with this graph as the solution of our equation y equal x squared? We did something called plotting points. We took whole number values of x near the origin, and plugged them into this equation, or substituted them in for x in this equation, to get the corresponding y value. For instance, I take -2 and substitute it into this equation for x squared. So I have -2 squared on the right. And what is that equal to? -2 squared. It's equal to 4. So that tells me that when x is -2 and y is +4, we have a solution to this equation. So what I did early on, I took the whole number of values of x near the origin, -2, -1, 0, 1, 2. And I took this value of x and I put it in the equation y equals x squared. If I take -2 and square it, I get 4, so that should be my y value. And I wrote that point down in the xy plane. Then I took this value of x, -1, and put it in the equation. -1 squared is +1. So when x is -1, x squared is +1, and that's what y should be equal to. So x equals -1, y equals +1. I wrote this point on the graph. And then I moved over again and I took x equals 0, put it in the equation. I squared x equals 0, I got 0. So that's what y should be. So I wrote this point, 0, 0, on the graph. Then I moved over a little bit more to the right. I took x equal 1 and put it into this equation. I took x equal 1 and I squared it, and I got 1. That tells me that when x is 1, x squared is 1, and that's what y should be equal to. Y should be equal to 1. So I plotted the point x equal 1, y equal 1 on the graph. And then I took one more x value, x equal 2. I put 2 in for x and squared it and got 4. And that told me that when x equals 2, x squared equals 4, but y equals x squared, so that means y is 4. So I took x equal 2, y equal 4, and I wrote that point on the graph. At this point, all I know for sure is that the points -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4 are points on the graph. All I know for an absolute certainty is that these 5 points are points on the graph. That's all I know for sure. What I'm guessing is that I can use these 5 points as the skeleton of my graph, and I can just cover that skeleton with skin and muscle to form a body. And how do I do that? I use my best guess as to what the body of this function should look like based on what the skeleton looks like. And to do that, I just connect the points. I realized that the points are not on a straight line. They couldn't possibly be. So I connect those points. And these points. And I surmise that for values of x greater than 2, this graph continues to go up. Do I know that for sure at this point? No, it's just my best guess. My best guess is that for x values greater than 2, the graph just keeps going up. And my best guess is that for x to the left of x equal -2, this graph continues to go up. So I put a little arrow here showing that the graph goes in that direction. I put an arrow here showing the graph goes in this direction. And this is my best guess for what the graph of y equals x squared looks like. At this point, that's the best that I can do. And what do I call this technique? This method of graphing an equation in two variables. This method of graphing an equation in two variables is called, whoops, I gotta get, this word is not in our vocabulary yet, please forgive me. But we're graphing an equation by plotting points. That's what we just did. But we take whole number values near the origin, whole number values of x near the origin, substitute them in for x in this equation, and we record the corresponding y value. As a matter of fact, I could have done this in a little bit more organized way. Here's what I could have done. I could have said, okay, I'll put my x values here. I'll put my y values here. And I'm going to record the corresponding y value for each x value. And as a matter of fact, I'll say y equals x squared over here. So when x is 2, when x is -2, x squared is -2 squared, which equals 4. So when x is -2, y is 4. When x is 1, I take, when x is -1, I put -1 in for x, and -1 squared is +1, so that tells me that when x is -1, y is +1. I take 0 and I substitute that for x, and that gives me the corresponding y value of 0. So when x is 0, y is 0. And then I take 1, I substitute it in for x, and when x is 1, y equals 1. And then finally, I'll take x equal 2, and I'll substitute it in for x. 2 squared is 4. So when x is 2, y is 4. And this gives me the points -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. have 5 points or 5 ordered pairs that I know are on the graph of the equation y equals x squared. So I plot each of these 5 points. They serve as the skeleton for the graph. And I use my best guess to fill in the muscle and the skin on that graph. And pretty much I do it by connecting the dots. These dots clearly don't lie on the same line. These dots must be on a curve. So I take a curve and I connect these dots. And that's my graph. That's my best guess as to what the graph of y equal x squared looks like. And at this point, this is the only tool that we have in our toolbox. The only tool for drawing the graph of an equation of 2 variables is plotting points, just like we did here. And I'll tell you something. It may be the case a year from now, when we're very good at graphing functions, that we may encounter a function that is so pathological that even then the only way we can figure out what the graph of the equation might look like is to plot points. Even a year from now, when we're really good at graphing equations, we might have an equation that's so pathological that the only way we can get an idea of what the graph of that equation looks like is to plot points. Right now, that's the only tool we have in our toolbox. So let's get some practice at using that tool. We'll do another example. Computing the graph of an equation of 2 variables by plotting points. Here's a nice example. We have the equation y equals 2x minus 1. And we're going to draw the graph of the equation by plotting points. And as we did in the example before, we're going to take whole number values of x right around the origin. Let's say -2, -1, 0, 1, 2. Whoops. And then we'll plot the corresponding y value. When x is -2, y equals 2 times x, -2, minus 1. So this is -4 minus 1 is -5. Holy moly. When x equals -2, y is equal to -5. When x is -1, y equals 2x minus 1. X is -1. So we have -2 minus 1 is -3. When x equals -1, y equals -3. When x is 0, we take x equals 0 and put it in the equation 2x minus 1. Then we have y equals 0 minus 1, that's -1. When x equals 1, we take x equal 1 and put it in for x in the equation y equals 2x minus 1. So y is equal to 2 minus 1, that's positive 1. And finally, when x is positive 2, we take positive 2 and substitute it for x. Y equals 4 minus 1 is positive 3. And that should give us enough ordered pairs. Let's see, what do we find out here? I'll tell you what. I'll put another column in my table. When x is negative 2, y is negative 5. Negative 2, negative 5 is a point on the graph. When x is negative 1, y is negative 3. Negative 1, negative 3 is a point on the graph. When x is 0, y is negative 1. The ordered pair 0, negative 1 is a point on the graph. When x is 1, y is 1. And when x is 2, y is 3. We have 5 points or 5 ordered pairs that we know are on the graph of y equals 2x minus 1. So let's plot these points. X equal negative 2, y equals negative 5. Negative 2, negative 5, does that look about right? Okay. Negative 2, negative 5. Let's plot this point. X equals negative 1, y equals negative 3. And is that, yeah, that looks good. Negative 1, negative 3. That's a point on the graph. X equals 0. Y equal negative 1. That's this point. 0, negative 1. When x equals 1, y equals 1. And when x equals 2, y equals 3. Here's x equal 2. Here's y equal 3. And now look at these 5 points here, 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 here. They look like they could be on the same straight line, and I'm guessing that that's what my graph is going to look like. Let's see if these points really do fall on the same line. By golly, I think they do pretty much. Yep. This is a very good guess as to what the graph of the equation y equals 2x minus 1 really looks like. So right now we have one tool in our toolbox as far as graphing equations of two variables goes. And that tool is plotting points. That's okay. We'll get other tools in our toolbox in time. But I'll tell you something. This is a tool that we're not going to want to remove from our toolbox. There will always be situations where maybe the first thing we should do when we're trying to determine what the graph of an equation looks like is plot a few points. So this is the only tool in our toolbox. It's fairly easy to use. We're never going to outgrow it. There will always be situations where the method of plotting points to draw a graph has great value. Now, are we going to draw some more graphs right now? No, believe it or not, we're not going to do that until the next section in our book. What we are going to do right now is just take a look at some special graphs and note the characteristics that they have that make them special. And note what this says about the solutions, the ordered pairs x and y. One important feature of the graph of an equation of two variables that we definitely want to be aware of and be alert to finding are the intercepts of the graph. There are two intercepts at most. We have the y-intercept. Maybe I should back up a bit. There could be more than two intercepts. The y-intercept of an equation in two variables is the point where the graph intersects the y-axis. The y-intercept intersects the y-axis. So the y-intercept is the point on the graph where the graph intersects the y-axis. And let's look at the example that we just got done doing. The equation y equals 2x minus 1. And if we remember, the graph crossed the y-axis right at the point x equal -1 and y equals 0. Let's see. Not being an idiot. Please forgive me. It crossed the y-axis at the point x equals 0, y equal -1. This is the y-intercept. And my little slip up a second earlier is even more unforgivable. When we consider what the y-intercept of the equation is, it's the place where the graph of the equation intersects the y-axis. But what is the y-axis? What is the y-axis? We discussed this in class yesterday. Let me clear some room to erase and I'll remind you of what we said. Remember in class yesterday, we observed that the y-axis is the set of all points or ordered pairs xy in the xy plane such that x equals 0. Every point on the y-axis is such that x equals 0. And it works the other way around too. If the x coordinate of a point is 0, that point is on the y-axis. So here's the y-intercept of our graph right here. Duh, the first thing I should have thought of was, oh, x equals 0. We're on the y-axis, x equals 0. And then I could have looked right here for the y coordinate. The y-axis is the set of all points in the xy plane such that x equals 0. So how do we find the y-intercept or the y-intercepts plural? How do we find the y-intercepts? Well, we know something. If a point in the xy plane is a y-intercept, then the x-coordinate of that point has to be 0. So to find the y-intercept or y-intercepts of a graph, substitute 0 for x in the equation, and then solve for y. Let's see if we can do that with this equation. Here's our equation. We substitute 0 for x, and that means that y equals -1. When x equals 0, y equals -1. So the y-intercept is the point 0, -1. Just like our graph showed. Now, in our book and on MyMathLab, when they ask for the y-intercept or the y-intercepts of a graph, they're probably not going to want it in this form. Well, why is that? Any point on the graph that is a y-intercept automatically has 0 as an x-coordinate. So if a point on the graph is a y-intercept, we already know that the x-coordinate is going to be 0. So probably the answer that they're going to want in MyMathLab, they're just going to want to know the y-coordinate. In this case, y equals -1. And that's a reasonable way to give the answer for a couple of reasons. One, like I mentioned, if a point in the xy plane is a y-intercept of our graph, we already know that x is going to be 0 at that point. So we just give the y-coordinate. Another reason why MyMathLab may want the answer in this form and just the y-coordinate is because at a y-intercept, the graph of the equation crosses the y-axis at this point. At this point on the y-axis, we don't give the x and y coordinate, we just give the y coordinate. See all of these points on the y-axis? Y equal -5, y equal -4, y equal -3, y equal -2, y equal -1. We haven't put down the x coordinate of any of those points because these points are labeling points on the y-axis. We already know that x is 0 there. So points on the y-axis are defined just by giving the y-coordinate. And where the graph crosses the y-axis, we're going to see the y-coordinate there. We're not going to see an ordered pair. This is not incorrect. But for a y-intercept, typically what we want is just the y-coordinate of the point. Because when we identify points on the y-axis, we do it by giving the y-coordinate. After all, we already know that the x-coordinate of a point on the y-axis is 0. Now, some of you may be wondering, and if you are, you're probably wondering for a very good reason. Since there is such a thing as a y-intercept, is there also such a thing as an x-intercept? And the answer is right. So you have been correct for wondering about that. Your intuition is taking you in exactly the right direction. There are such things as y-intercepts, and there are such things as x-intercepts. So we'll talk about that in just a second. X-intercepts, here we go. The x-intercept of a graph of two variables is a point where the graph intersects the x-axis. So an x-intercept is a point where the graph of the equation crosses the x-axis. How would we find such a point? Well, remember what the x-axis is. Since the x-axis is the set of all points in the xy plane such that y equals 0. Yep. Any point on the x-axis has a y-coordinate of 0. And any point that has a y-coordinate of 0 is on the x-axis. So, since the x-axis is the set of all points in the xy plane such that y equals 0, we can find the x-intercepts by substituting 0 for y in the equation and then solving for x. That's how we do it. So let's look at the same example that we've been working with for the last 10 or 15 minutes. Same example. Y equals 2x minus 1. Now we want to find the x-intercepts. And we reasoned, let's see, the x-axis is the set of all points where y equals 0. So to find the point where the graph intersects the x-axis, set y equal to 0 and solve for x. Except I didn't quite say it that way. I said substitute y equals 0. Okay, we just substituted 0 for y, and now we're going to solve for x. Move the 2x over to the left, and then divide both sides by -2. Our x-intercept is 1/2 0. The point x equal 1/2, y equals 0. And for the same reason why we usually don't identify the y-intercept with an ordered pair, we won't identify the x-intercept with an ordered pair either. My math lab is probably going to want us to write the x-intercept this way. One half is the point on the x-axis where the graph will cross the x-axis. We already know that at the x-intercept, y is 0. So this doesn't really tell us anything that we don't already know. And let's see how this squares with the graph of the function that we had already plotted. Here's the graph that we've been working with for the last 20 minutes or so. Great example, by the way. We're getting everything that we can out of this. And we remember our y-intercept is at y equal -1. Our x-intercept, according to this, is at the point 1/2 on the x-axis. Does that seem right? Let's see. Here's the origin, 0. Here's 1. And right smack in the middle between 0 and 1 is 1/2. Yep, here's our x-intercept. Here, as we already knew, our y-intercept. So how do we find x-intercepts? What did we do? Substitute 0 in for y and solve. How did we find our y-intercept? Since x is 0 on the y-axis, to find the y-intercept, we substitute 0 for x and solve for y. And by the way, if you don't already use the expression plugging in, you no doubt will adopt that custom very quickly. I'm not saying I like the expression. I'm not saying I dislike the expression. But instead of saying substitute for a variable, it is the custom, the practice of every student in the United States to use the expression plug in. So instead of saying substitute, we'll say plug in. And apparently, this expression came from the idea that we have some hole here that we need to fill. And to fill it, we take any number and plug it in here. So whenever we substitute a number for x, or whenever we substitute a number for y, it's common for us to say that we're plugging in. I'm not saying I like that expression. I'm not saying I dislike that expression. But that expression is in such overwhelmingly common use that to try to avoid using that expression would be to try to swim against a tidal wave. You can't do it. So from now on, instead of saying substitute 0 for y or substitute 0 for x, I'm going to swim with the tide and I'm going to say plug in 0 for x or plug in 0 for y, or plug in some other number for x, or plug in some other number for y. Let's consider this example. Y equals x squared minus 1. And since we know what intercepts are now, let's find these first. Intercepts are a valuable tool in graphing functions because they tell us where the graph of the function, I'm using that word again. Finding the intercepts is a valuable tool in graphing equations of two variables because it tells us where the graph crosses the y-axis and where the graph crosses the x-axis. And the x and y axes are our frames of reference in the xy plane. Every point in the xy plane is given in reference to the y-axis and the x-axis. For example, the point 0, 0, the origin, that's where the x and y-axis intersect. The point 1, 5 is the point that's 1 unit to the right of the y-axis and 5 units above the x-axis. Everything that we do in the xy plane is done with reference to the xy axes. So finding the y-intercepts and the x-intercepts is an important step for us to take in graphing an equation of two variables. So let's see, find the y-intercepts, plug in 0 for x. We plug in 0 for x, and we get y equals 1. No, we don't. There, that's better. Y-intercept. Y equals -1. So on my graph, I'm going to make sure that I plot that point. Now find the x-intercepts. And to do that, to find the x-intercepts, we plug in 0 for what? For y? So that means we have 0 equals x squared minus 1. Plug in 0 for y. And let's move the x squared to the left. Negative x squared equals -1. Okay, let's multiply both sides by -1. And now I just compute the square root of both sides. But when I compute the square root of this side, what do I have to be careful to do? It's going to have two roots, right? A positive root and a negative root. Plus or minus square root of 1. So x equals -1 and x equals +1. Those are our x-intercepts. Now it just so happens that these were points that we were going to plot anyway. So let's see, x equals -1, y equals 0, x equals +1, y equals 0. And what about the y-intercept? Y is -1 when x is 0. And let's just compute these other 2 points. X is -2. We plug in -2 for X. -2 squared is 4, minus 1 is 3. And now let's take X equal 2 and plug that in for X. 4 minus 1 is 3. X is -2, Y is 3. That's a point on the graph. X is -1, Y is 0. X is 0, Y is -1. X is 1, Y is 0. X is 2, Y is 3. These are the points that we're going to plot, and we already have at least some of our, no, we have all of our intercepts. We sure do. Because we solved for the intercepts first and got all of them. We got the 2 X-intercepts, we got the 2 Y-intercepts. So we have all that there are. Now let's graph this son of a gun. Okay, let's graph this equation, y equals x squared minus 1, and plot the points. X equal -2, y equals 3. So that is way the heck up here. X equals -1, y equals 0, so that's right here. Y equals 0, x equals x equals 0, y equals -1. X equal 1, y equals 0. X equal 2, y equals 3. Holy moly. I guess that doesn't look too bad. Not bad. And, you know, the more I try to improve this, I think the worse it's going to get, so I'm going to leave it like that. And notice what we have. X-intercept, Y-intercept, and then the other X-intercept. This is kind of interesting. We had 2 X-intercepts this time. It can happen. So we plotted this graph, plotting points, but we also made sure that we included the X-intercepts and the Y-intercept. And that's important because it ties our graph in with the frames of reference that we have, namely the y-axis and the x-axis. This equation is almost exactly like the one we just got finished graphing. The one we just got done with was y equals x squared minus 1. This is y equals x squared plus 1. let's graph this equation. And the first thing I want to do, because these are so important, is make sure that I find all the intercepts, the y-intercepts, the x-intercepts. For the y-intercepts, we plug in 0 for, let's see, on the y-axis, x is 0. So for the y-intercepts, we plug in 0 for x. Was that easy or what? And this turns out to be one of the points that we're going to plot. X equals 0, y equals 1, y-intercept. So 0, 1 is an intercept. Let's do our x-intercepts now. And to get x-intercepts, let's see, the x-axis is the set of all points where y equals 0. So to get the x-intercepts, we plug in 0 for y. Okay. So that means 0, plug 0 in for y, equals x squared plus 1. I'll move the x squared to the other side. Negative x squared equals 1. And I'll multiply both sides by negative 1. X squared equals negative 1. I'll compute the square root of both sides. And remember, there are two roots here, plus or minus. The square root of negative 1 that's I, an imaginary number. It's not real. So there are no real x-intercepts. What on earth does that mean? You know what it means? If we did have x-intercepts, they'd be points on the x-axis. Is plus I a point on the x-axis? You know, it isn't, because the x-axis is a copy of the real number line. That's all the x-axis is. It's a copy of the real number line laid out horizontally. So the only points on the x-axis that we have are real numbers. This is not a real number. So in the xy plane, there are no x-intercepts. I wonder what that means. Well, no x-intercepts. I guess what that means is that the graph of this equation just never intersects the x-axis. The graph has to be above the x-axis or below the x-axis, but it never crosses the x-axis. I think that's what this is telling me. Let me get some more points to plot, and maybe this will all make sense. X equals -2, I'll plug in -2 for x. So we have 4 plus 1 is 5. X equals -1. We plug in -1 for x, and we get 1 plus 1 is 2. X equals +1. We plug in 1 for x. So y equals 1 squared plus 1 is 2. Okay. X equals 2. Plug in 2 for x. Y equals 2 squared plus 1, which equals 5. Let's draw a picture of this thing and see if that ties all the loose ends together. Okay, let's plot these things and see if it will all make sense. X is -2, y is 5. X is -1, y is 2. X is 1, y is 2. X is 2, y is 5. These are the points that we're going to plot. -2, 5. X is -2, y is 5. That looks good. X is -1, y is 2. Here's -1 on the x-axis. There's y equal 2. Yep, looks good. X equals 0, y equals 1. Here's our intercept, our y-intercept. X equal 1, y equals 2. Here's x equal 1. Y equals 2. And finally, x equal 2, y equal 5. Here's x equal 2. And here's y equal 5. Do I like that? And I just connect the dots. And that's pretty much what the graph of this equation looks like. And now I can see why we looked for x-intercepts and didn't find any. We looked for x-intercepts and we got imaginary numbers. The values of our x-intercepts were not real numbers, which means we didn't have any. So maybe that's a lesson learned. We didn't get any x-intercepts because there weren't any. This graph lies entirely above the x-axis. It never crosses the x-axis. So if we're looking for x-intercepts and we get imaginary numbers, or if we get complex numbers, that tells us the graph doesn't cross the x-axis. There are no real roots, no points on the x-axis where the graph of the equation crosses the x-axis. So if we're solving the equation, plugging in 0 for y, and we get imaginary numbers or complex numbers. It means ain't no x-intercepts. And it happens. It happened here. All it means is that the graph of the equation lies entirely above the x-axis, or in other cases, the graph of the equation may lie entirely below the x-axis. And since the graph never intersects the x-axis, we don't have any x-intercepts. Now, let's take a look at something called symmetry. Another important thing that we'll consider about graphs is symmetry. And there are different kinds of symmetry. Let's consider symmetric with respect to the y-axis. An equation in two variables is symmetric with respect to the y-axis exactly when this occurs. Whenever the point xy is on the graph, the point negative xy is on the graph. And let's illustrate this with our example y equals x squared plus 1. The example we just got done with. Negative 2, 5 is a point on the graph. And positive 2, 5 is a point on the graph. Take 2, plug it in, we get 5. Take the negative of 2, plug it in, we get the same y coordinate, 5. So if 2, 5 is on the graph, negative 2, 5 is on the graph. And it seems to work for all of the points on the graph. 1, 2 is a point on the graph, and negative 1, y equal 2 is a point on the graph. And x equals 0, 1 is on the graph. What about negative 0? Well, that's just 0, right? So 0, 1 is a point on the graph. Negative 0, 1 is a point on the graph. They're the same point. But this graph the graph of this equation is symmetric about the y-axis. And I'm about to tell you something about the graph of an equation that's symmetric about the y-axis. An important visual observation. A couple of things here. I defined an equation in two variables being symmetric with respect to the y-axis. Sometimes we say, whoops. Sometimes we say symmetric about the y-axis. So if an equation is symmetric with respect to the y-axis, sometimes we say it's symmetric about the y-axis. And here's an observation that I want to drive home. Look at this graph. This graph is symmetric about the y-axis. And notice something. The part of the graph that lies to the left of the y-axis is the mirror image of the part of the graph that lies to the right of the y-axis. This part of the graph is the mirror image of this part. This part of the graph is the mirror image of this part. And that's true of the graph of any equation that's symmetric about the y-axis. For any equation that is symmetric about the y-axis, the portion of the graph to the left of the y-axis is the mirror image of the portion of the graph to the right of the y-axis? Well, if the graph of an equation can be symmetric with respect to the y-axis, could the graph of an equation be symmetric with respect to the x-axis? The answer is yes, and we'll look at that. If there's such a thing as symmetry about the y-axis, there's also such a thing as symmetry about the x-axis. An equation in two variables is symmetric with respect to the x-axis or symmetric about the x-axis exactly when this happens. Whenever the point xy is on the graph, the point x negative y is on the graph. So if we plug in y and get x, and then we plug in negative y, we're going to get the same value of x. Here's a function that's symmetric about the x-axis. X equals y squared plus 1. And I plug in all of I did something sneaky here. I plugged in the y values, squared them to get my x values. So when y is negative 2, x is 5. So 5, negative 2 is on the graph. When y is negative 1, x is 2. So 2, negative 1 is on the graph, and so forth. And let's see. When y equals 0, we have our x-intercept. Y equals 0, x is 1. So 1, 0 will be our x-intercept right there. That we plot all of these points, and notice something. When I plug in negative 2 for y, I get 5 for x. When I plug in positive 2 for y, I get 5 for x, the same value. When I plug in negative 1 for y, I get 2 for x. When I plug in positive 1 for y, I get 2 for x, the same value. So if I take y and plug it in, I get this value of x. If I take negative y and plug it in, I get the same value of x. That means that the graph of this equation is going to be symmetric about the x-axis. And look at it. Whoops, 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 whoops. I got an error right here. Yep. I got errors here. Say, this point y equals negative 1, x equals 2. This point y equals negative 2, x equals 4. Okay, I feel a lot better now. I feel a lot better. And notice what goes on. These 2 points have the same x coordinate, 2, but different y coordinates. Y equal 1, y equal negative 1. When we plug in this value of y, we get x equal 2. When we plug in the negative of this value, negative 1, we still get x equal 2. When we plug in 2 for y, we get 4 for x. When we plug in the negative of 2 for y, we still get 4 for x. This graph is symmetric about the x-axis. And know something. The portion of the graph above the x-axis is the mirror image of the portion of the graph below the x-axis. And visually, that tells us when the graph of an equation is symmetric with respect to the x-axis. For any equation that's symmetric about the x-axis, the portion of the graph that lies above the x-axis is the mirror image of the graph that lies below the x-axis. This portion of the graph above the x-axis, it's the mirror image of the portion that lies below the x-axis. The graph of this equation, x equal y squared plus 1, is symmetric about the x-axis. Now, are there other kinds of symmetry that we can consider? Yeah, one more kind. But before we do, let's see how we go about showing that an equation is not symmetric about an axis. One way that we can do it is just to look at the graph. And if one part of the graph is not the mirror image of the other, then it's not symmetric about an axis. On the other hand, we can determine if a graph is not symmetric about the x-axis by plugging in strategic values of x and y. Is the graph of this equation y equals 2x plus 3 symmetric about the x-axis or the y-axis? There are a couple of ways that we can go about doing this. One thing that we could do is just plug in values of x and y. And if we get lucky, well, let me put it this way. If we suspect that the graph is not symmetric with respect to either axis, maybe the way to go is just to plug in a few values of x and y and see what happens. Let's say that I doubt that the graph of this equation is symmetric about either axis. I'll plug in a value of x, I'll plug in the negative of that value, and if I don't get the same value, the same y value for each of those x values, it's not symmetric with respect to the y-axis. So let's see. So when x is 1, y is 5. What about x equal negative 1? Negative 2 plus 3 is 1. We took an x value, plugged it in. We took the negative of the original x value and plugged it in. We didn't get the same y value. For x equal plus 1, x equal plus 1, x equal minus 1, we get different y values, not symmetric about the y-axis. What about with respect to the x-axis? We'll try y equal 1. And so we have 1 for y equals 2x plus 3 And I guess I can subtract 1 from both sides. When y equals 1, x equals negative 1. Let's try y equals negative 1. We plug it into this equation, y equals negative 1. And I'll add 1 to both sides. And then I guess I'll move this 2x over to the left. And then I guess I'll divide both sides by negative 2. X equals negative 2 and y equals negative 1. Okay, so what does that tell us? I plugged in y equal 1 and y equal negative 1, but I didn't get the same x values. So it's not symmetric about the x-axis. Now that was one way that we could have done it. Another way that we could have done this was just to graph that equation and say, is the portion to the left of the y-axis the mirror image of the portion to the right of the y-axis? Is the portion of the graph above the x-axis the mirror image of the portion of the graph below the x-axis? Let's take that approach. Let's do this all over again, but let's do it graphically. Another way that we can see if the graph of this equation is symmetric about either the x or the y-axis, just draw a graph of the thing and see what it looks like. And we'll take our old friends for x coordinates, -2, -1, 0, 1, 2, those look like good candidates. And we plug them in, and y is equal to 2 times -2 plus 3. And that's what? -4 plus 3 is -1. Holy moly. We'll take -1 and plug it in. -2 plus 3 is +1. Plug 0 in. Plug in 1. Five. Plug in 2 for x. So that gives us ordered pairs -2, -1. -1, +1. 0, 3. 1, 5. 2, and 7. And now we'll graph this son of a gun. Let's see, y goes from -1 to 7. And let's plot these babies. X is -2, y is -1. X is -1, y is +1. X is 0, y is 3. And what's that? -1, 1. Okay. X is 1, y is 5. X is 2, y is 7. And let's see. I guess this point was a little bit off. Here's the graph. Is the part of the graph that lies to the left of, is the part of the graph that lies to the right of the y-axis the mirror image of the part that lies to the left of the y-axis? No. If this part were the mirror image of the part that were to the left of the y-axis, the graph would have to go like that. And then we'd say, oh, you know what? This is the mirror image of that. But this doesn't happen. Okay. Is the part of the graph that lies above the x-axis the mirror image of the part that lies below the x-axis? No. If the top part were the mirror image of the part that lies below the x-axis, then this graph would go like that. And this part would be the mirror image of that part. But that doesn't happen. Clearly, this graph is not symmetric with respect to either the x-axis or the y-axis. Now we have one more type of symmetry to talk about. The last point of symmetry that we're going to talk about. The graph of an equation in two variables is symmetric with respect to the origin. Or, you know, they used to spell symmetric with a C. Symmetric about the origin whenever this happens. If xy is a point on the graph, then -x, -y is also a point on the graph. And here's a classic example of an equation that's symmetric about the origin. To graph this, we're going to plot some points. X equals, y equals, xy. And we'll take our old friends, -2, -1, 0, 1, and 2. X is -2. We plug that in for x, and y equals -2 cubed, which is 8. No, it's not. -2 cubed, which is -8. . Plug in negative 1 for x. Y is negative 1 cubed, which is negative 1. Plug in 0 for x. Y is 0 cubed, which is 0. Plug in 1 for x. Y is 1 cubed, which is 1. Plug in 2 for x. Y is 2 cubed, which is 8. And let's see what we get for ordered pairs. Negative 2, negative 8. Negative 1, negative 1. 0, 0. 1, 1. And 2, 8. Now notice what's going on here. Take these two coordinates, negative 2 and negative 8. Change the sign of both. I'll tell you what, let's start down here. Take these two coordinates, 2 and 8. Make them both negative. And guess what? Negative 2, negative 8 is also on the graph. Let's try this one. Take these two coordinates, 1 and 1. Make them both negative. We got negative 1, negative 1. That's also on the graph. Well, take these two coordinates, 0 and 0. Make them negative. We still get 0, 0. So it looks like whenever xy is a point on the graph, negative x, negative y is also a point on the graph. And in fact, it is. And let's see how this looks graphically. It's not going to hit us in the face like symmetry about the y-axis or about the x-axis. But we're going to look and see what symmetry about the origin really means. This is the graph of our function. This is the graph of our equation, which is symmetric about the origin. And graphically, here's what that means. This is the characteristic of the graph of an equation that's symmetric about the origin. If you take the portion of the graph above the x-axis and flip it over, let's see. Take this thing and flip it over the x-axis. And let's see, I didn't do a very good job of that. That's a little bit better. So let's see. Flip the portion of the graph that lies above the x-axis. Flip it about the x-axis. And that's what we did. That portion will be the mirror image of the portion of the graph that lies below the x-axis. So take this part of the graph that lies above the x-axis and flip it over the x-axis. And what we're going to get is something that's the mirror image of the part of the graph that lies below the x-axis. That's probably the simplest way of explaining what this means graphically. Okay, everybody, we've been good boys and girls. Let's go home and rest for a while, and I'll have some homework assignments waiting for you.